We're going to look today at work and energy, three types of energy specifically: kinetic, potential, and elastic. So let's say we have a particle traveling along this curve from S1 to S2. We have an origin and a position vector r to the particle, and the particle has a force acting on it, force vector F. So dr in green, this is going to be tangent to the path at our angle theta. So we can denote an increment of work as dW, and we'll define it as work equals our force vector F dot dr. Now, F dot dr is going to be equal to the magnitude of F times the cosine of theta times the magnitude of dr. So the total work done, we can say, is going to be the integral of F dot dr from S1 to S2. Now, there's a couple things to note about work. So work is a scalar, meaning it has magnitude but no direction. It can be positive or negative. It's going to have units of force times length, so pound-feet or Newton-meter. And the most important two things to remember about work is that work is only done in the direction of displacement. And that makes sense. If you look at our equation, we have this angle theta, and we're taking our, the cosine of theta. That's where this component comes in here. So we're only looking at the direction of our displacement, and that's the only way that we're going to have work. And the other important thing to note is work is going to be equal to our force times our distance when our force is constant. So those are the two most important things to keep in mind when we're going through these types of problems. Let's look again at force with Newton's law now. So F equals ma, and we could also say mv dv ds. And we're going to separate our variables. So F ds equals mv dv. And let's integrate from S1 to S2. v1 to v2, mv dv. And one more step here. So this is going to give us 1/2 m v1 squared plus s1 to s2 of f ds equals 1/2 m v2 squared. So this is an important equation. So when we're looking at this, we can say, here's our work in the middle between 1 and 2. And this component here, this is going to be what's called our kinetic energy at state 1. And this right here is going to be our kinetic energy at state 2. So we can even write this simpler as a scalar equation. So we can say the energy at 1 plus the work between states 1 and 2 equals the energy at 2. And this is what's known as the work-energy equation. So our kinetic energy, we know, is going to be equal to 1/2 mv squared. So there's our kinetic energy. Our potential energy, this is the energy that an object has based on its displacement or position. So if you have a ball on the ground and the ground is your datum, or I'm sorry, if you have a ball that's thrown up in the air at some height h with a mass m, your potential energy is going to be equal to mass times gravity times height. And we can call Ke our kinetic energy, and we're going to call our potential energy Pe. So our kinetic energy we can say as Ke, and our potential energy we're going to call Pe. And the last type of energy is our elastic potential energy. And we're going to call this EE. And this is the potential energy an elastic object has that has the ability to store energy or do work. So these types of problems are mostly, you're going to see a spring. And with springs, you're always going to have a spring constant K, and that's going to measure the spring stiffness. So if you have a force P pulling on this spring, you're going to displace it by some length, and we're going to measure that by delta. So however much this is displaced from its original unstretched length is going to be delta. And you could graph this just to show that the force and the elongation are proportional. So if you felt so inclined, that would look like so, where we have our force on our y and our delta on the x. And you would find that you would have a slope equal to our spring constant. So again, this just shows that our force and elongation are proportional, and that would allow you to even write that P, our force, equals the spring constant times our displacement. So we're going to write elastic energy as 1/2 K delta squared. So now we have an equation for each one of these energies. And the most important thing to remember is that we're always going to have conservation of energy. The kinetic energy of state 1 plus the potential energy of state 1 plus the elastic energy of state 1 plus the work from 1 to 2 is going to be equal to our kinetic energy of state 2 plus our potential energy of state 2 plus our elastic energy of state 2. So this is our conservation of energy equation, and this is just a good way to double check yourself as you go through and solve your problems, because you're always going to have energy conservation. Thank you for watching. If you like this video, please be sure to give it a thumbs up and subscribe. That really helps support my channel and helps me continue making videos for you guys. I'll see you next time.